Against all odds, I'm still Cooper, and this is still machine learning, and today we're going to be doing something practical. So, let's go over a little bit of what we've been doing. Alright, so here's our new definition of machine learning as it stands. We will use data to tune parameters of a model, which will be initialized with hyperparameters, to minimize a loss function that measures how poorly it matches some function. We might even want to call this a data distribution, as we'll see at some point, but for now we'll just call it a function. Now, something you might have noticed in the coding in particular, but while I've been talking about it, is that we use two different data sets when we're doing our tasks. We use a training data set, but we use a testing data set when we're actually seeing how well our data works, how well our model works. But why do we do that? I'm going to let you ponder it. You might be able to come up with some good answer, actually. It's a neat intuition if you have it already. If not, we're going to be going over it. But I want you to think about why that might be. Do like genuinely take a minute, pause the video, and just give it a think. You come up with some very interesting thoughts when you actually do that. I always like doing that on my YouTube videos. Alright, so let's continue. So let me tell you why. So let's take an example. Let's do a proof by example. So here is some random data, very little data, but it could be more data if we wanted it to be. So what we're going to do is we're going to define our model. Here is a simple model. We're doing the 3 different parameters. We're having a weight matrix on X, weight matrix on I guess just weight values in this case. Weight value, and we have it with X squared here. So now the question is that I want to pose to you is, what's the best possible fit we could get out of this data and this function? I'll let you think for a second. Think about the order of the function. So we have a square on our data here, our model here. I want you to think about how we could best fit it. That was a hint, I guess. And of course, I will start answering now. We can use a parabola to fit our data. So you can see sort of where the parabola would sit, like here, and you can see a poor drawing of it right there. So you get the idea, is that a parabola would actually fit it better. There's no straight line that would really get them all, but we could, if we do it correctly, get all 3 of these data points with our parabola here, which seems nice. I mean, that's nice since passing through all the data. And, you know, it's the best possible fit, especially if we're hitting all of the data points. That's 0 loss in a lot of these cases, so that's very good, right? But let's look at what the rest of the data is. So this is just the data we've been given, and let's imagine we get the rest of the data now, and let's fill it in. Not so great all of a sudden. This looks like a really bad fit. So it's actually sort of bamboozled us, and instead of it being along this curve like we predicted, it's actually right here. It's just a distribution around this line. So what we notice from this is the idea that if we fit too well to the data we're given, then we can't generalize to the data we're not given. You can think of more extreme cases. Perhaps if we had a high polynomial here, we could go through all of these like super precisely, but then as soon as we got any piece of data that wasn't one of the ones we're given, it would perform terribly. This idea that, you know, if we fit too well on the data we're given, we won't generalize, is called overfitting. And this is a very important concept in machine learning, so definitely make sure you understand the intuition here and make sure you understand what that term means. If you don't immediately understand what it means, I'd say pause the video, rewind, watch it over again, and try to explain it to yourself. Try to understand it as best you can. Convince yourself that this is a big deal. Come up with cases even, but definitely understand this. All right. I won't be covering it too much more, which I apologize about, but there are other things I want to cover instead. All right. So let's talk about the training paradigm, like how we go about training, which is related. What we normally do is we have a training data set and we have a testing data set, and this is sort of intuitive from what I've been saying, but we will only train on the training data set. We assume that we are not given the test data set. In a lot of these cases, we have a test data set, so you might be asking, why don't we use it? Really what that is simulating is the idea of doing the task without knowing what you're going to have to actually see. So you can imagine like a self-driving car. They have their training data, but their test data is just running it. They don't actually get to test it. So this is an important paradigm, that the test data set is essentially off limits while we're training, but we do get the trained data set as much as we want. So we're going to judge our performance solely off of how well it does on test. We can analyze how well it does on the training data, and that's interesting in its own right, but that is not how we measure its performance. We measure it off the test data set. If our model does well on the test data set, then we say that it generalized well. So it did a good job of taking this training data and interpolating it and saying, okay, this is like how this data works, and then when we get the test data set, if it works well in it, then we've generalized well. If instead it does well on the trained data set, maybe even very well on the trained data set, but does poorly on the test data set, then most likely our model has been overfit to the training data, almost always. That would be the case. So, those are the two things we're looking for. We're looking at the interaction between how well this performs and how well this performs, and we can sort of say things about our model based on it. All right. So that is the paradigm. And now we want to talk about an issue that we have sort of been avoiding. We haven't talked about it at all. I've hinted at it perhaps, but we haven't really talked about it at all. So we have, this is our current network that we've been working with. We have our convolutional neural network. It looks nice and all that. We have our hidden layer with its size. We have these convolutions with their strides and their kernel sizes and all of that. We have our stochastic gradient descent with its learning rate. And what we're starting to see is that we have a lot of hyperparameters. We started with maybe a couple, and of course I've mentioned batch size and stuff, there's even more, but we started with like one or two, and now we're sitting at like a dozen different hyperparameters that we need to take care of. We need to understand what they're doing, and we need to set them to something. We need to decide how to do that. So I pose the question to you, how do we know the best ones? I know you can't quite see in the video, but I'm asking you, how do you know the best ones? Right? So give that a think. And after you give it a think, I'll give you an answer. Maybe a dissatisfying one, but we'll see. So let's talk about this right here, model validation hyperparameters. But let's say, how do we know the best hyperparameters? So we have the examples here, learning rate, hidden layer size, and there's a bunch more. I mean, I just gave you a couple examples, but there are a bunch we've found so far. And the answer is, we don't know the best ones, in fact. And this is a big problem. This is a big problem. We don't know what the ideal learning rate is for us. We don't know how big our hidden layers should be. We don't know how big our kernel should be. It all seems all of a sudden like guesswork, which to a degree it is, but we want to be scientific about this. We want to find some method of doing this properly, all right? And this is where hyperparameter searches come in. There are other ways that we're not going to cover right now, but we're going to talk about hyperparameter searches, and we're going to talk about validating our model, all right? So these are the two tricks we're going to use to be able to figure out what our hyperparameters should be. All right, let's talk about the first. All right, so this is an example of how we might run a hyperparameter search. In this case, this is a grid search, which is essentially checking different combinations of values of our hyperparameters and seeing how well it performs. Let's see how it looks. So we'll have a for loop for our learning rates through different values. We'll have a for loop through our hidden node values, different values we could have. I'm only doing the two hyperparameters, but we could have as many as we want. And we go through, and with those parameters in mind, we'll make our network with these values. Then we'll do our optimizer. Again, we need our learning rate here. So we have our hidden nodes and our learning rate have both been used. And then this right here represents us training the model on the data, and then testing, validating the data. We could use a test data set here if we so choose. And then recording which one performed the best and recording which values are associated with that. So what we're going to do is essentially do 9 different iterations of making the network, training the network, and then comparing it to our best performance. And then from that, we'll get which one of these combinations works the best. Now, you might be thinking to yourself, oh, that seems awfully slow, and what if we want to have like 6 different variables? Then won't we have 3 to the 6 different runs of it, and won't that be insanely slow? And you're right. This is not a great method of doing it, but it is a method of doing it, and it is actually one of the better ones to do it nowadays. This is a big problem. Finding the best hyperparameters is a big kind of open problem. There's a lot of different techniques, but this is the simplest and kind of most common approach. Let's talk about something else, though. Let's talk about, I said validate your model here, but what does that mean? Let's talk about it. So validation is a specific little clever trick that we can do where we're going to use the training data set to test. So we're going to take like our normal paradigm of training data and testing data, and what we're going to do is we're going to split up our training data into training data and also validation data. So what we're doing here is we are restricting the amount of training data we have even more, but we're giving ourselves a nice way to validate the training data without ever needing to touch the test data set, because we are not allowed to touch it. So we can essentially treat this validation segment of our training data as the testing data set. So we can actually do, like in this previous part, we can actually do a validation of our data set and see how well it generalizes instead of just seeing how well it trains, which is not super helpful. All right. So that idea, which is clever in its own right, leads us to something a little bit more interesting and something that is, in practice, a little bit better, which is K-fold validation, which is a type of validation. So we have this before. This is how we take a simple validation from our training set, and we use that as our validation. And what we're going to do instead is we are going to separate our training data into a bunch of different segments, into different training segments. And what we're going to do is we are going to choose one of these training splits, we're going to call them splits, one of these training splits as our validation data. And then we're going to use the rest of them to train. So at one, like if we were to do this, we might choose, okay, 2 is our validation set. We're going to train using 1, 3, 4, 5, and then validate using 2, and see how our performance is on that. See how well it scores on this one. What we're doing when we're doing K-fold is we're going to do every iteration of that. So we're going to use validation, and we're going to use train 1 as our validation first, train off these, see how it does. Then we're going to use 2 as our validation, check them all, then 3, and so on. And then we're going to average the performances over all of the possible validation sets, and we get some value, and I want to point out at least that we're going to reinitialize our model in between these so it's not cumulative. We're going to like train on each of these individually, and then we're going to do that. So this is called K-fold validation. The K comes from the number of different validation sets we have. So if we had this right here is 5-fold validation, so we're doing 5 different folds. And then we can use this to test our model. So let's do a little run through of how this might look, what the structure looks like. So we'll have, like before, we'll be searching over these 2 hyperparameters. So we're just doing the same thing over these 2 hyperparameters now, but we're going to have a new for loop. This for loop is going to be the different folds that we have. So we're going to do k different folds, right? So in each of these, we are again going to create our network, create our optimizer like before, but we're going to add a new segment here where we are going to get a training data and validation data by doing a split along our training data with our value k. So we'll determine what our validation should be and what our training should be from this function here that we'd have to code if we want to use. And then from this, we're going to do our same thing before, where we're going to train on this training data set using our optimizer, and then check on the validation, and then we're going to actually average these over these k different iterations here, and then see how well it compares. After we do that, we see which one of these combinations of hyperparameters worked the best, and then we can choose that model. The benefit of doing this K-fold validation is that we will actually end up with a much more general model by doing this instead of just picking some validation chunk out of ours. We'll have to generalize to every single different validation set we use. And we can also pick our k. It's another hyperparameter, ironically. It's like a hyperparameter. So we have to pick our k, and we can choose whatever we want to get different operations from here. One interesting thing you might think is, what if we choose k to be equal to the amount of data we have, which would mean that we only have a single data point as our validation set. And this is actually an interesting and useful idea. So I'd recommend you think about it a little bit what that would do. and see if maybe that is a good idea or not. This wraps up our K-fold talk and all of that. Next time we're going to do a bit more coding, and we're going to look at a more rigorous example, and we are actually going to be doing some parameter tuning and see how well we can get our model working. See you then.